Okay, so what we're going to be doing today is taking an algebraic approach to solving vector problems. Yesterday, we learned how to solve these problems using drawings, and we saw the limitations in using drawings. Everyone produced slightly different drawings based on the level of accuracy they were capable of doing, and we had slightly different answers. So today's approach solves all that and makes sure that we all have the exact same answer. And the way we're going to do that is by using trigonometry. So trigonometry will ensure that we all have precise answers. Sound good?
Yeah.
All right.
Great.
So let's take a look at this first example where we have two vectors, 200 meters east and 300 meters north. We want to add these two vectors up and find the resultant displacement. So if you add them up tail to tip, you will see that they form a right-angled triangle. And the answer is the hypotenuse of this triangle. So we'll call this hypotenuse total displacement. So how can I use trigonometry to find total displacement? Good. We'll use the Pythagorean theorem. And for this, I'm going to label this so that we know what we're talking about. The hypotenuse is C, one of the sides is A, and the other is B. So Pythagorean theorem states that C squared is equal to A squared plus B squared. We want to find the magnitude of side C. So we're going to take the square root of both sides, and we know that C is equal to the square root of A squared plus B squared. If we sub it in using the values that are present in the question, 200 meters east and 300 meters north, we end up with the square root of 200.0 So we've set up Pythagorean theorem to solve for the magnitude of the hypotenuse. We punch it into our calculator, and what do we get? Mr. Billion.
361.
So to one decimal place, 360.6 meters. Is that cool? Good. So I can say that the total displacement is 360.6 meters, except I'm missing something. There's a piece of information that is critical that I'm missing.
Direction.
The direction. So to report the direction, I need to see which direction this vector is pointing. It will be helpful if I could find out what theta was. Now, if I know trigonometric ratios, namely SO, CA, TOA, and I know that B is the opposite and A is the adjacent, can I find the unknown angle theta? What can I use, Alex?
You can use TOA, but the only thing is you'll have to rearrange it.
So tan theta is equal to opposite over adjacent. Tan theta, therefore, if we sub in these values, the opposite is 300 meters. The adjacent is 200 meters. So we have 300.0 over 200.0. When calculating the angle, you do not need to put any units in. We're just looking at the ratio of these two numbers. Now, how do I actually get a theta value from my calculator? I want the actual angle. Try to use your calculator and tell me what we need to do in order to get an angle. Do you remember how to do this? Practice. Try something out. Guy, what do you have to do to your calculator to get this answer?
You have to do the tan inverse.
So you have to find the inverse tan. So what we're doing, if you take a look up here, the angle is going to be equal to the inverse tan of this ratio, 300.0 over 200.0. So what you need to do is 300.0 divided by 200.0, second function tan. And if you do that, what angle do we get, Anthony?
56.3.
Good. 56 degrees. Report your decimal, report your angle to 2 significant digits. Don't report any decimal places. You're fine.
What if it's like 60?
For the simplicity of this lesson, we're just going to keep it at. You don't have to round up.
Or like two significant digits?
No decimal places,
Okay.
for clarification. Yeah. Okay, so we found the angle, but we still haven't reported the direction. How do I report what direction this is? If you take a look, this red line is 56 degrees up from the horizontal. What direction is that? How do I report that? Alexa? Good. 56 degrees to the north of east. Question?
Could you also say like 34 degrees?
Yep, but in this example here, we found theta. So since we found it, you're going to report to this. You're right that there are two directions for each possible case, but there's no sense in making an extra step to find the alternative angle for this. So just report using the one that you find. It'll save you time. And stick with that. Yes?
I don't remember how to get from the second last step to 56.
So you're going to type in 300 divided by 200. Then hit second function, tan. So double check that your calculator's not in degree mode, or that it is in degree mode, sorry.
I think you have to press equals and then.
In this next example, we have a vector, and the vector is 30.0 meters. (25 degrees north of east). Now, this vector here can be broken up into components that go east and west and components that go north and south. So even though this vector is pointing in some direction that is not east or south, we can actually break it up into simpler components. So what we're going to learn how to do in this section is how to break up a vector into horizontal and vertical components. So if we do that, the horizontal component of this vector would be this segment right here, which I'm tracing in blue. This horizontal component we're going to call the x component. If we call the original delta D, then this horizontal component will be delta dx. The vertical component of this vector is this line that I'm tracing in green. This vertical component I'm going to call delta dy. So this red vector, delta D total, is exactly equal to the sum of the blue and the green. These two vectors are identical to this one red. Okay? So we have to learn how to find the size of this part of the vector, which is the x component, and the size of this part, which is the y component. So in order to do that, we're going to label these hypotenuse, opposite, and adjacent. How do I know which is the hypotenuse, which is the opposite, and which is the adjacent? The longest side is the hypotenuse. If we find the angle, the side that is directly opposite the angle is called the opposite, and the one that is right attached to the angle is called the adjacent. The term adjacent means beside. So let's first determine the x component. The x component is going to be given the symbol delta dx. Some textbooks won't put an arrow on top of this because the x tells you the direction. The x tells you that it's horizontal. I like to keep the arrow on top. So we're going to find the x component. In order to do so, I'm going to use the adjacent and what is known, the hypotenuse. So adjacent and hypotenuse. Can anyone tell me what relationship that is? Anthony?
Cosine.
Yep. Cosine theta. So let's replace adjacent, hypotenuse, and theta with the symbols that we know. So the adjacent is delta dx, the hypotenuse is delta d, and theta is 25. I'm going to use colors. Delta dx over delta d is equal to cos of 25 degrees. So the whole purpose of this was actually to solve for the x component, delta dx. How can I rearrange this statement to find just delta dx? What can I do to this delta d, Matt?
Move delta D over and multiply by cos 25.
Good. So we end up with delta dx is equal to delta d times the cos of 25. What do I put in for delta d here? What does the original question tell us? Delta d is what, Megan?
30 meters.
30.0 meters times the cos of 25. Let's punch this into our calculators, and let's see what we get for delta dx. Everybody practice, because this could be tricky depending on how we have to use our calculators. Selena. Good. 27.2 meters. Is there a direction? Fantastic. East. And the whole point of doing this is to break it down into very straightforward, easy directions like north, south, east, or west. So all of your x components will be either east or west. And all of your y components will be north or south.
When doing trigonomic functions, do we assume that the output of the trigonomic function has an infinite number of signigs?
Yes, for example, when you're multiplying it by this trig ratio, assume that that does not affect the accuracy of your number, because this is an accepted ratio. The cos of 25 is and always will be whatever the cos of 25 is. Good question. Okay? Okay, let's set out to determine the y component. Once you've done a couple of these, it'll become really quick to do. So this is the green. Determine the y component, which we will label delta dy. So when we're looking at the y component, this green arrow is the opposite in this triangle. So if we're looking at the ratio of opposite over hypotenuse, what trig ratio are we looking at? Opposite and hypotenuse. Megan? Good. If we rewrite this relationship with the symbols that we use, we have delta dy over delta d is equal to sine of 25 degrees. So we're still solving for delta dy. How do we rearrange this? Just as we did in the previous example, to get it by itself, Jordan?
Multiply delta g by sine 25.
Good. So this is going to equal delta d times the sine of 25. We know that delta d from the original question is 30.0 meters times the sine of 25 degrees. Punch that in your calculator and tell me what you get. What is the y component of this vector? Nick, what'd you get?
14.7.
Good, 12.7, and can you give me a direction? Amazing. 12.7 meters north. So what we did was we took a vector that was kind of pointing a little bit east and a little bit north, and we found out exactly how much of it is east and how much of that vector is north. And we broke it up into simple x and y components. Now we can use these x and y components to solve questions. Instead of looking at the original vectors, what we can do is actually break up all vectors into just x's and y's. And when we do that, we can add up all the x's and add up all the y's algebraically, because anything x will be collinear, and anything y will be would be collinear as well. So in sample problem number 3, we have a cat walking 20 meters west, and then walking a further 10 meters, 40 degrees east, south. And we want to find the total displacement. Now, since these are non-collinear vectors, we would have to use the tail-to-tip method. But let's practice using component vectors to solve this problem. So for this example, we'll use component vectors. If we didn't use component vectors, remember that we would have to employ the tail-to-tip method. So what's the first step? I'm going to draw a reasonable diagram of what these look like. The first vector, delta D1, is 20.0 meters west. And the second vector, delta D2, is about 40 degrees to the east of south and is 10 meters long. So it looks like this. So we're going to have to break these two vectors up into their x and y components. Let's take a look at vector 2 for a moment. You can see that this vector has some x component and some y component. So some horizontal component and some vertical component. What you have to do is break it up into these vectors. For the sake of keeping it the same, I'm going to make this y component green, and I'm going to make this x component blue. And I'm going to label these components delta dx and delta dy. Now I started with this one because it's one that looks most like the previous example, where this vector here can be broken up into an x and y component. But there's something different about the other vector, delta d1. Does it have any vertical component to it? No. So all of this vector is the x component. So I'm going to label this delta dx. So since we're looking at vector 1, I'm going to call this specifically delta dx1. And since this is vector 2, I'm going to call this delta dx2. Similarly, this green vector, I'm going to call delta dy2. Alexa.
Since are we just keeping in mind when like graphing that horizontal lines are x and vertical lines are y, that's why?
Yep, absolutely. So I gave them the symbols x and y because I'm mimicking what we use in the Cartesian plane, x being horizontal and y being vertical. So not by accident, on purpose. Okay? So if I want to find the total displacement of these two vectors, what I have to do is add up all the x's, then add up all the y's, and see what I get. So let's do the first step. Let's add up all of the x components. If I add up all the x components, the total x is going to be equal to delta d x1 plus delta d x2. Less u. So I know delta dx1. I know that delta dx1 is 20.0 meters west. But I haven't calculated what delta dx2 is. I know from trigonometry that this is the opposite side of this triangle with respect to 40 degrees. And if I know the hypotenuse is 10, I can say this statement. Now stop and watch me write this. I can say that delta d x2 is equal to 10.0 meters times the sine of 40 degrees. So what I did was all of the steps that I've done in the previous example, but I did the rearranging right away. So it ends up being 10.0 meters, which is in our original question, times the sine of 40 degrees. If you punch that into your calculator, what do you get? Megan?
6.4.
6.4. And what direction would you say that's in?
East.
Good. 6.4 meters east. Very good. So to find the total x, we add 20 meters west plus this x component of vector 2, which we said was 6.4 meters east. Can we add these two algebraically? Are they collinear? Are west and east along the same straight line? Yes. What must we do before we do that? Express them both in the same answer. So in order to do so, we're going to rewrite these so they're in the same direction. I'm looking at this, and I know that if I change this to east, I won't end up with a negative number. Or this to west, rather. So we end up with 20.0 meters west minus 6.4 meters west. If we punch this into our calculator, what is our total x component? Anthony?
15.6 meters west.
Good. So we're going to do the same now, but add up all of the y's. We know that from our original question, vector 1 doesn't have any y component. Only vector 2 has a y component. So the total y component is equal to just delta d y2. This y component from vector 2. So your job is to determine what delta d y2 is using trig. So if we look at this green vector that we've drawn, this represents the adjacent side to the angle 40 degrees. If we have the hypotenuse and we use the adjacent side, what trig ratio is that? Cos. And here's the little trick. If the x component is sine, then the y component is going to be cos, or vice versa. If this were pointing in a different direction, if the x component was cos, then the y component is going to be sine. So I can quickly write 10.0 meters times the cos of 40 degrees. Punch this into your calculator and tell me what you get. Alex?
7.66 meters north. Wait, I mean south.
Good. 7.66 meters south. So the total y is 7.66 meters south. So now what? We found all our x's and we found all our y's. What we do now is we add those two together to make a simple right-angled triangle. So if we add those two together, make a simple right-angled triangle. I know that the y component is 7.66 meters south, and I know that the x component is 13.6 meters west. My final answer to this question is this vector. I've done all of this work to find the magnitude of this. How can I find the magnitude of this now? Good. We're going to use the Pythagorean theorem, which states that delta D is equal to the square root of 13.6 squared plus 7.66 squared. Punch it into your calculator and give me the answer to one decimal place. Selena? 15.6, do we concur? So we're almost done. The one piece of information that remains is the direction. I know that it's kind of pointing some angle to the west of south. So some angle to the west of south. But I need to determine what that angle is. Just as I did in the previous example, I'll use the opposite and the adjacent sides to determine this angle. Opposite and adjacent are from the trig ratio tan. So to find theta, it's equal to the inverse tan of 13.6 divided by 7.66. Punch this into your calculator, everyone. Practice using this method.
What does it say? Theta.
The inverse tan.
Oh.
Or
Megan?
do you want two decimal?
No decimal places.
61 degrees.
Sure. Are we sure it's 61?
Yeah.
Okay. So 61 degrees to the west of south. So instead of employing the tail to tip method, we have employed component method to solve the same question. If we would have used the tail to tip, we would have finished it really quickly. What is the problem in doing that method, however? It's inaccurate because everyone's drawing is going to be slightly different. Okay? So this method's tedious, but remember the steps. Break each vector into x and y components. Add up all the x's. Add up all the y's. Then make a simple right-angled triangle and use Pythagorean theorem to solve for your final answer. There are a few homework questions for you to practice this technique. Make sure you do these.